first place, I thank the organizer for this nice opportunity to present our work in this conference. I'm from the Instituto de Física Rosario. Rosario is a city in Argentina. I think I am the only speaker in this conference of the Southern Hemisphere. And this work was done in collaboration with Ignacio Pomponio. He's a PhD student in Rosario, and some colleagues in Rosario, Adolfo Trumper and Claudio Gassa, and also colleagues here in the USA, Colo Gioldi, who is present here, and Christian from Tennessee, Shanshun Tang from Minnesota, and Josie Camilla from Shanghai, China. The works I will present are published in this work last year, and there are also some work in progress. Essentially, my talk is very related with the previous one. I will talk about anomalous spin dynamics in triangular antiferromagnet, concentrating in one compound, in this cobalt compound. Here is perhaps the main result of this talk. Using a theory based on Schwinger bosons, Schwinger boson representation of the spin operator, we can reproduce the experimental results of inelastic neutron scattering. Here the outline. First I will present the anomalous, why the magnetic excitation in the triangular antiferromagnet we consider are anomalous, in what sense. Then I will talk a little about this cobalt compound, its main features, and I will show some neutron scattering spectra that they show a strong quantum effect in comparison with a semi-classical approach. Then I present our theory, that is the Schwinger boson theory beyond the saddle point or the middle field approximation. That is the usual procedure to do with the Schwinger bosons. Then I will show the comparison between experimental results and our theoretical result. And finally, if time permits, I will talk a little about the temperature evolution of the magnetic spectrum with the magnetic spectrum. Let's begin with some non-frustrated quantum antiferromagnet in 2 dimensions. The classical square. Okay, thanks. The classical square lattice, there the quantum ground state is the semi-classical usual Neal order of 2 sublattices. Their elementary magnetic excitation are also semi-classical spin wave, and here is some comparison between the magnetic spectrum in the curve price and linear spin wave. The solid line is the linear spin wave prediction, the points are the experimental results, and there is an excellent agreement between semi-classical approach and the experimental result, the experimental observation. No? But what happens in the triangular Heisenberg antiferromagnet that is frustrated? No? Well, as it was said in the previous talk, Anderson was the first to propose a quantum spin liquid for this quantum antiferromagnet. In particular, he proposed a resonating valence bond quantum spin liquid. But then, later, several numerical works have shown that the frustration in the triangular lattice is not enough to destroy the semi-classical order. So the quantum antiferromagnet on the triangular lattice, on the Heisenberg antiferromagnet, has a 120-degree Neal order, a series of lattices magnetic state, but with a much reduced local magnetization as compared with the classical one. Only 30% of the classical moment survived to the quantum fluctuation. Okay, so the ground state of the triangular antiferromagnet is a semi-classical state, a 120-degree Neal order. However, the quantum excitation, the elementary magnetic quantum excitation, are not the semi-classical one. No? The linear spin wave theory does not reproduce the main features of the magnetic excitation. For example, here there is a comparison between the solid line that is linear spin-wave magnetic dispersion along some highly symmetry direction in the hexagonal Brillouin zone. They are the series expansion result, the numerical series expansion result are compared with the linear spin-wave. So the solid line is the linear spin-wave prediction, and the dots are the series expansion ones. We can see two main features that are of not semi-classical nature. One is that there is a strong downward renormalization of the bandwidth of the magnon, nearly 30% with respect to the independent magnon. And also there are some rotor minima located at the midpoint of the Brillouin zone edge, this B or M point, that cannot be reproduced with a semi-classical approach. Well, okay, but why this happened in the triangular lattice? Why we have a semi-classical ground state, but non-semi-classical quantum excitation? Well, the reason is that the triangular antiferromagnets is ordered, but it is very close to a quantum critical point, to a quantum melting of its long-range magnetic order. In fact, here is a very generic phase diagram in terms of some G parameter that control fluctuation. For example, it can be the second near neighbor exchange interaction and temperature. So if the Heisenberg antiferromagnet is in this nil order phase with a little second nearest neighbor exchange interactions, J2 of the order of 6% of J1, the system goes to a quantum spin liquid. Almost all people believe that this region is, in the particular case where G is the J2, this is a quantum spin liquid. There are some controversy about the nature of this quantum spin liquid, if it is a gap 1, a C2 quantum spin liquid, if it is a gapless U1 Dirac spin liquid, but almost all people agree that here there is a quantum spin liquid instead of a quantum valence solid or a valence bond solid or something like this. Well, so in the nil order, in the left part of this phase diagram, the magnetic excitation we expect are magnon 1, semi-classical 1, but in the right part, the magnetic excitation consists of deconfined spin-on with a spin 1/2. So our hypothesis is that perhaps the magnon of the 120-degree nil order can be described as bound states of two-spinon excitation. This is our hypothesis, because, as I showed you before, the semi-classical approach does not reproduce the magnon excitation very well. Okay. So we are trying to describe the magnet excitation as, this is a very cartoon, or as a bound state of two spinon. Okay, so we go to this material, this cobalt material. It is believed to be an almost perfect realization, experimental realization of the spin 1/2 triangular lattice. It is a equilateral triangular lattice. There is no spatial anisotropy as in another system. Also, it is quite isotropic in the spin space. In fact, the G factors are almost isotropic. The saturation magnetization is also almost isotropic. And from high magnetic field measurement, it is, as Stanislav told in the previous talk, a nonlinear spin wave can reproduce very well the spectra at high magnetic field, and from this fitting, it is known that the XXZ model is a very well theoretical model to treat this system. The anisotropy is relatively rather small, It's only 6%, the exchange anisotropy. This is easy plane anisotrope. No? Okay, here are some inelastic neutron scattering spectra from two groups, Tanaka and Koldea, along this direction in the hexagonal Brillouin zone. There are some features, important features that differ from the semi-classical magnon. First, there is, as I said, the white line corresponds to the linear spin wave. First, there is the strong downward renormalization, and also the magnon are not quite sharp as in semi-classical approach, and the most important feature is the extended continuum and structured continuum above the magnon, the single magnon excitation, no? The two single magnon branches. No? And this continuum extends up to 6 times the J1 interaction, no? The exchange interaction. Well, okay, these are all, another inelastic neutron scattering spectra for different directions. This is along the C direction that shows that it's almost that the exchange interaction between different layers are very, very weak. Well, here it's a cut for the M point in the Brillouin zone. This is energy and intensity. There are 3 stages in the experimental spectra. Oh. Sorry. Okay. There are 3 stages. The first consists of the single magnon branches, then a second one, and a third one at the highest energy. Okay. As I said before, one of the main features that differ from the semi-classical magnon excitation is that the continuum excitation has a much stronger weight than the single magnon dispersion. No? There are 3 times more continuum excitation, that spectral weight in the continuum than in the 2 branches of the single magnon. Okay. When instead of using the linear spin wave, the people go one order further, considering 1/s correction. The agreement also is good. No? The magnon bandwidth, even in the nonlinear spin wave, when they are considering magnon-magnon interaction, is too large, of the other 30% greater than the experimental one. The magnon are too sharp, and the continuum has a very, very low intensity in comparison with the experiment, no? 4 times lesser. Here is a cut, energy, momentum cut, so you have the 2 branches in the nonlinear spin wave, the 2 single magnon branches, and the continuum is very low in comparison with the spectral weight of the single magnon excitation. Well, so what we have done is, instead of using a semi-classical approach, we come from the other extreme, from the very quantum with a very quantum picture. That is, consists in representing the spin operator by a Schwinger boson with 2 flavors, spin up and spin down, in order that, well, sigma is the usual vector of Pauli matrices. In order this to be a good representation of the spin, an exact representation of spin operator, we have to impose a local constraint to the number of Schwinger bosons. That can be seen as a nether charge of some gauge symmetry that has the theory due to this partonic approach. Well, when we replace in the exchange term this Schwinger boson representation, we can rewrite the exchange interaction in terms of some bilinear operators, B and A, where they have a very simple, a very intuitive, we can see them in a very intuitive way. The operator A creates singlets on a vacuum, while the operator B make that the singlet resonate, make the singlet to move. No? So these are the basic ingredients of the resonant valence bonds theory. Okay, what we do next is we use a path integral approach to compute the partition function. The minus sign are not here. So, and we put an external source and an external magnetic field in order to compute the dynamical spin spectra. And also, and this is a central point of our theory, we have to put a very small magnetic field with the same pattern as the 120-degree order in order to explicitly break the SU2 symmetry of the Hamiltonian. No? The Schwinger boson theory without this little magnetic field is an SU2 theory. The magnetic order is obtained as a Bose-Einstein condensation of the Schwinger boson, but there is now a selection of some of a fixed magnetic pattern. No? In order to reproduce the experimental result, to obtain finite result for our further saddle point calculation, it is necessary to include this magnetic field. Well, then we replace the interacting Schwinger bosons by independent Schwinger boson coupled to Hubbard-Stratonovich field using the Hubbard-Stratonovich transformation, the conventional Hubbard-Stratonovich transformation. When we do this Hubbard-Stratonovich transformation, the bosonic action, the partition function can be written as an integral over the Hubbard-Stratonovich fields, the dynamic Hubbard-Stratonovich field, plus the lambda is a Lagrange multiply that enforces the local constraint of the number of bosons. And this is an affective action that has been obtained integrating out the boson. No? So the boson are now, they do not interact each with the other, but they are coupled to a fluctuating to a dynamical Hubbard-Stratonovich field, whose phases are gauge fields, no, that emerge in this Schwinger boson representation. And to compute the partition function, we have to integrate over all the possible Hubbard-Stratonovich configuration. Okay. Well, what we do with the partition function? Well, we make a large n expansion. We extend the spin up down to an index that goes from 1 to n, no? Because in the large n limits, the saddle point approximation of the effective action is exact, no? And so what we do is we perform a saddle point approximation, and over this we compute the first 1 over n correction, no? Also called Gaussian correction. No? Well, as I said before, if we do not include the symmetry breaking magnetic field, the spin-on dispersion are gapless in 4 points. This is unphysical. No? So we have to include the little magnetic field to gap out 3 of these modes and to leave only 1 gapless spin-on dispersion point, no? in the gamma point. An essential point of our theory is that the 1 over n correction to the spin dynamic is finite only if we have a condensation of the Schwinger boson. No? If we have a long-range magnetic order at this level of our approximation. Okay, so we expand the effective action in the saddle point plus the Gaussian fluctuation, delta phi phi the Hubbard-Stratonovich field, W conjugate, and lambda. We replace in the path integral, and at the Gaussian level, we can make this integral, no? And in this way, we can calculate the partition function as a function of the external sources we derive with respect to these sources, and we obtain the dynamical spin susceptibility, no? In terms of Feynman diagrams, the saddle point spin susceptibility is this bubble where the open circle are what we call external vertices. It has to do with how the Schwinger boson couple with the magnetic external field, while when we consider 1/n Gaussian correction, this is the Feynman diagram. We have to include this counter diagram. Why counter diagram? Because at the saddle point approximation for computing static properties is a relatively good theory. However, if we use the saddle point approximation to compute dynamical property, the dynamical spin susceptibility, the saddle point approximation is essentially wrong. Why? Because it can be shown that the relation dispersion is given not but pole related with Magnon excitation, but instead is given by pole related with the spinon, the single spinon, no? And collective excitation is not a single spinon, but it is a Magnon. So in order to correct this wrong behavior, we have to include this 1/n diagram that exactly cancel out the saddle point single spinon pole, no? And we obtain the Magnon pole correctly. Well, here is an example for some momentum. The dashed line corresponds to the saddle point approximation. These two are single spinon poles. The 1/n correction is the blue one. When we zoom the dashed at the blue, we have the Gaussian fluctuation spectra that consists in only a single Magnon mode, no? In the physical Magnon mode, no? And this Magnon mode consists of two spinon bound states, no? In fact, in saddle point, we have two peaks, no? We can show that this peak is spurious. It had to do with some bosonic density oscillation that are unphysical because and they appear at the saddle point approximation because the constraint in the local number of boson is included not in a very well way. Okay. So we make this 1/n correction to a saddle point approximation, and we compute, for example, the local magnetization, the staggered magnetization. In the saddle point is 0.28. With the Gaussian fluctuation correction, it goes down to 0.22. That compares very well with the numerical result, quantum Monte Carlo del d-emergy, no? These two numbers exactly coincide, but they are not very independent, no? It's because in the d-emergy you see the quantum Monte Carlo result to obtain some characteristic of the cluster that they have used, no? But overall, we have a better agreement with numerical results than in the saddle point approximation, no? Also, we compute the spin wave velocity in our approximation, and we have a very good agreement with a nonlinear spin wave result for both spin wave velocity, no? One characteristic that is wrong in the saddle point approximation is that the spin-on velocity are the same for both Goldstone modes, no? For the gamma and the k point. And we know that they should be, for a non-collinear state, they should be different as it happened in our correction, in our theory. Okay, and then we compare the dynamical magnetic structure factor along some direction in the hexagonal Brillouin zone. This is the experimental result. This is our theory. We capture correctly the single magnum branches, the two single magnum branches. In the saddle point approximation, there are three single magnum branches. One of them, as I said before, is spurious, has to do with some unphysical density fluctuation. We also have an important two-spinon continuum. The relative weight of the continuum with respect to the spectral weight of the magnum is 2.74. That compares very well with the 2.8 of the experiment, and it is rather better than the 0.66 of the nonlinear spin wave theory. Okay, here I have a comparison between, well, the same as before, as experiment and our Gaussian fluctuation corrected result, and also the saddle point approximation. As I said before, there are three branches. The intense region corresponds to single spinon pole and not to the physical magnum pole, and all this is corrected when we include the 1/n diagram. Okay. Well, here is the comparison for another direction of the Brillouin zones. We have the correct bandwidth renormalization. In our theory, we have not. We are using the exchange interaction and the anisotropy obtained from the experiment. We have the correct spectral weight distribution between the single magnum excitation and the continuum. But there is something bad, is we do not recover the Roton minima. The experimental Roton minima does not appear in our theory. We think that in order to recover this Roton minima, we have to perform some vertex and self-energy correction to the spinon dynamic. No? In our theory, we have the free spinon of the saddle point approximation, and we bind together, they interact through the Haber-Turner fields, and they bind together, but in order to reproduce, we think that in order to reproduce further feature of the experiment, we need to go further to include another 1/n Feynman diagram. Okay, and with respect with the high energy excitation, this first stage of the continuum is well reproduced by our theory. However, the highest energy stage is not reproduced at all by our theory. No? Also, we think this has to do with the lack of vertex and self-energy correction to the spinon dynamics. Okay, well, here I pass this. Here is a cut for the M points. The dots are the experiments. The solid line is our theory. So we reproduce relatively well the first branches, magnum branch. The second one, no. The first continuum is reproduced rather well, and the extended, the highest energy continuum, no. So our theory gives a good description of the experiment, but it lacks several features, and we think that we can improve on this. Okay, well, this has been shown before. Well, and finally, I will show some temperature evolution of the magnetic excitation with temperature. Here is the T equals 0, the ground states. When we increase the temperature, the magnum excitations get mixed with the continuum that has a thermic origin at a temperature of the order of 0.7 of the Nil temperature. Well, here we are working with the layered triangular antiferromagnet. No? We include some interlayer in order to get a finite Nil temperature. So at a temperature of the order of 1.7 times the Nil temperature, the only magnum that survives, well-defined magnum, are only the one closest, closer to the Goldstone mode, no? Closer to the Goldstone mode, and until at the Nil temperature, all the magnum disappear as well-defined quasi-particle. Here I have some cut for this momentum, where this is the violet is the ground state result with a well-defined magnon, at the black one is the one corresponding to a mean temperature where there is no magnon dispersion. Well, so the conclusions, we think that the spin dynamic of the triangular antiferromagnet is better described using a free spin-on gas at the starting point. We are not saying that we are seeing a free spin-on in the magnetic spectrum of this cobalt compound. No? We are saying that as a starting point, it's better to begin with a free spin-on gas than instead of a free magnon gas, as in semi-classical approaches. The magnon excitation are recovered as two-spinon bound state in our theory. The binding is provided by the emergent gauge field of the theory. The continuous, we can see the continuous excitation as two quasi-free spin-on states. No? And finally, as the temperature increases, only the magnon close to the Goldstone mode survive up to the new temperature. Well, thank you.
Thank you. Are there any questions?
Luis, thank you for a wonderful talk. So I'd like to clarify, could you show again the comparison between the saddle point and the corrections? Yes, this would do, okay. So if I look at the middle panel, could you elaborate, so where should I see the two fictitious peaks instead of one?
Okay, here, bueno, if you look, it looked very similar, no? However, we have to make some cuts for different momenta to see perfectly the difference between saddle point and here, for example, and the Gaussian corrective result. No? The saddle point has, for this momentum, has these two peaks, no? That correspond to the dispersion relation of the single spin-on of the theory. No? One of these peaks, it can be shown that is related with some density, and physical density fluctuation of the Schwinger boson. No? Because when we impose the constraint, we impose, instead of a local one in each site, we impose a global constraint. So we are not, in the saddle point, it's worse the situation, we are not putting on, for example, for the spin 1/2 case, we are not putting exactly one boson in each site, we are putting n boson in an n lattice site. Also, at the saddle point approximation, there are a lot of unphysical density fluctuation, and this fluctuation gives rise to a spurious peak in the saddle point. But when consider Gaussian correction, the density, this is result shown by Auerbach in the 90s, the density susceptibility goes to exactly zero due to this 1/n correction. So the constraint is better imposed, and also the 1/n term works as a counter diagram that exactly cancel these two peaks of the saddle point approximation and give rise to a true magnon pole, two magnon mode, this red resonance.
But if I may just clarify, so let's stay for a second at the saddle point level, yes. Right? So you have 3 sublattices, you have 3 species of Schwinger bosons.
We work in local axis, so we are working with only one species of Schwinger boson. In each side, we have the same operator, the same boson operator, with the two flavor up and down. No? We are working in the structural hexagonal brilliant zone. No? We are not folding in the magnetic brilliant zone.
I see. So let me just make a point quickly. Sorry, I don't want to, maybe we could discuss this later. What I wanted to ask is the following. So if you have a certain number of sites per unit cell, whether you fold it or not, right? That's how many species of Schwinger bosons you've got. So after you do the Bogolubov transformation, after you do Haber-Stratonowicz, you transform to a new basis of quasi-particles, your Green's function are going to have exactly the same number of poles as the ones you started from. So let's say you have 2 particles per unit cell, like in an AL antiferromagnet, you're going to have 2 poles. So what puzzles me is how come you seem to have 2 spurious peaks instead of 1? But we can discuss later. I don't want to belabor the point. Thanks.
Yes, thank you, Luis. One technical comment. I mean, that diagram is a 1/n correction, that tail that we showed, only in absence of a condensate. In presence of a condensate, there is a singular contribution that is of order 1, and that is basically what cancels the poles, the single spin-on poles of the saddle point diagram. So.
This is a strange 1/n expansion, no? Because this diagram is of order 1, this diagram is theoretically or formally of order 1/n, but due to the condensation of the bosons, when we replace one spin-on propagator, this spin-on propagator with the condensated one, and also this, we get a contribution of order 1 that exactly cancels the saddle point approximation.
So in your plots of the dynamical structure factor, you showed, I understand, the total response with all polarizations added up.
Yes.
Can you comment on the polarization of the continuum with respect to the polarization of the magnons?
If I remember well, the continuums come from the, essentially, from the in-plane fluctuation. The CC component has lesser continuum than the in-plane component. No?
Well, I'm wondering if this could be used experimentally to distinguish between 2 magnons or 2 spin-ons.
Unless to order 1/s in spin wave theory, it is almost impossible to obtain this broad spectra that go from 0 to nearly 6 times the exchange interaction. So even considering the 2 magnon processes, no?
Sure, but it would be nice to have a really qualitative distinction.
Yes. We think one way to distinguish between 2 magnon and this picture is that we are working in this now is to include the magnetic field and to look the magnetic response of semi-classical theory comparison with our theory that it will have a very different response because this boson has a spin, no? So they couple with the magnetic field through the sigma term. No?
Thank you.
So could you probably have done this calculation, right, for the other material, so if you look on isotropic Heisenberg model?
This?
Yes. Right. And so...
sorry.
So can you comment on relative intensity of the continuum in that case, in your calculation?
Well, in this case, this is the experimental in this ytterbium compound, the experimental spectra. I have to make some remark. These Schwinger boson theory results are obtained at 0 temperature at the ground state. No? So we have some magnon dispersion that is not seen in the experiment. The experiment is performed at almost the nil temperature. No?
So theoretically, so the spectral weight in the, continuum versus single particle, the single magnon weight.
Yeah.
Do you remember?
I don't remember, but if we make this calculation at this temperature, probably it's all a continuum, a diffuse continuum. All the spectral weight goes to the continuum part.
But also one difference, this is for Heisenberg, not for...
Okay, this is a Heisenberg compound, but with a J2 interaction that makes the system very closer to the quantum critical point than the cobalt compound.
Yes, okay. And then, small question. So in your calculation, when you do your 1/n corrections, So the spin waves that you obtain, do they have, are they delta function like modes, or they have some line widths?
Yes.
They are delta.
One thing I didn't say that if we go to the large S limit, we recover exactly the linear point result in the dispersion and also in the spectral weights. No? We have analytically, it can be shown that we have the same linear speed wave result. No?
Okay, thank
Yeah. Sasha?
So just to follow up, I think from the previous talk and from Oleg's question, it's clear that the value of delta is deviates seemingly insignificantly from 1 for the case of the barium cobaltate, and yet the intensity change. Okay, there is J2, of course, but the intensity change in the continuum is drastic from what you show in your theory and what was shown in experiment for the isotropic J1, J2 case. Is there any insight into that?
As you say, in this cobalt compound, the only role of the anisotropy is to open this gap. No? When we go to the triangular and to the isotropic, perfectly isotropic, there is more continuous. No? There is more isotropy. When you go down, when you increase the anisotropy, the system behaves more in a semi-classical way. No?
One insight is that we suspect that intermediate peak is basically an overdamped longitudinal mode. In the Heisenberg limit, you have 2 gapless modes, 2 Goldstone modes. When you put a small XXZ, you gap one of them, and you're removing one channel for decay of the longitudinal into transfer. So we suspect that that's the reason why the structure emerges only when you put a small easy plane anisotropy.
I'm rather concerned about the spectral weight. Yes. I mean, it's just, even if you have decays, don't you expect it's going to be broadened, but
in the Heisenberg limit, you still have very large spectral weight. What you miss is the structure.
It moves down. Okay.
Yeah.
Are there any more questions? I have just a small question. So you mentioned at the beginning, to stabilize because you have an ordered state and you're decomposing into Schwinger partons. How big of a field do you need to actually?
Of 1 over the number of sites.
Okay, so very small.
Like in the textbook where you have to compute the order parameter, including a very small symmetry breaking field. Then we go to the thermodynamic limit, and after that, we take the limit of this H field to 0.
So it immediately stabilizes the...
Yes.
Can you also comment on the improvement of the sum rule going from...
Yes. In the saddle point Schwinger boson theory gives a very wrong sum rule, 50% incorrect. With the inclusion of this 1 over n diagram, the difference between the exact results, the integral of the spectrum the integral in omega should be equal to s times s plus 1. With the inclusion of Gaussian fluctuation, we go from the 50% difference to a 20% difference. No? There is a lot of room to improve the theory, but we think we are in the correct way, including this kind of 1 over n diagrams.
All right, thank you. If there are no more questions, then let's thank both speakers again.